Alright, we're doing some more approximating the distribution of the sample proportion. Alright, and we are in particular looking at the normality of the sample proportion. That's p hat for large sample sizes, n, and various values of population proportion, lowercase p. And this is our learning goal, where we're trying to understand by considering the approximate normality of the distribution of the sample proportion for large samples. So we understand that we use or rely on samples and then hence sample statistics like p hat, for example, to tell us things about the population. Okay, so we use samples to tell us things about the population and statistics from samples to tell us things about the population. So, especially for large populations, are impossible or impractical. We don't have enough resources, okay? And so things like p hat, the sample proportion, okay, that becomes an estimator for the population. Okay, we know that. But what if the samples are too big too? Like in practice, we usually deal with really big, very big populations, but also big samples. So we could be doing sample sizes of 100 or 200, and then we could have multiple samples of each of those. So multiple samples. Okay, that in practice that happens, and we might be looking at hundreds. Like there might be, for example, 200 samples of sample size 100. That's in itself really big, and it really reintroduces that same issue of large populations, that we don't have the resources to get right on top of all of that. So what in the world do we do? Is sampling just a waste of time? Well, the answer is no, because we're going to investigate a few things which can alleviate this concern. And at the same time, we're going to look at the distribution of the sample proportion. Okay, so looking at what do we do with really big numbers, and doing that via looking at how the distribution of p hat changes. So what we have here is that let's suppose we know that 55% of the population have a certain characteristic of interest to us. Okay, so p, lowercase p, would be 0.55 based on all the previous work we've done here. And for each of these dots, you see in this first dot plot, it doesn't look like much, does it? What they've done here is it's a sample size of 100. So each of these dots is a calculation, like this one here, for example. Well, I've drawn over it slightly, but it's at 0.58. Now that would be a single situation of 58 over 100 were noted to have a certain characteristic of interest. So that would be 0.58. This one back here would be 0.44, so 44 out of 100 taken would be our sample proportion. So we have a sample size of 100. And we took 10 such samples. We can't really see much from that. What if we increase the number of samples? So we've got sample sizes of 100 here, and we've got a lot more than 10. Alright, we've got quite a few more. You can see that. We have actually 200 samples here. And each of those dots is a sample size of 100. Okay, so this one, say here, one right on the top, right there, okay, just the top one, that's at 0.61. That would be an individual sample of 100 and 61 in that sample had the attribute or the characteristic that we're after, so that would give us the 0.61. Okay, we've got 200 of those, and then if we repeat it, we don't necessarily get absolutely identical results here, but both of them fit a normal distribution as we increase the number of samples taken. Alright, so, and we have a good, or increase the sample size, we have a lot of individual samples there, and we get the normal distribution. Okay, and all behave. So the normal distribution itself can vary because the standard deviation can be larger or smaller, and the actual mean can vary too, but they're still normal. Okay, so that means that we can be on top of, even when samples are large and the resources are limited, we can still be on top of this because we know its behavior if we take large enough samples. Okay, if we have enough sample data, if we have enough of these population proportion calculations, we know that it behaves as a normal distribution quite well. Now it should make sense because in a previous video we've established that when n is large enough, the distribution of a binomial random variable can be approximated by a normal distribution, and that's what this is, because if the thing we're sampling has the characteristic, it's counted as a success. So from all our previous work we can model it for binomial or Bernoulli style model. But because it's large enough, we, just like with the binomial random variable, we can approximate these sample proportions, the distribution of the sample proportions, with a normal distribution. Okay, so it can be done with a normal distribution, provided we have enough samples. Okay. Remember, you should have watched that last video or so that covered this, but the rule of thumb is if n times p and n times 1 minus p are both individually greater than 5, everything's okay. And so we can, for a situation similar to the data we're looking at here, what if we had for NP, well, n is 100, and so p, the mean is 0.55, so we'd have 0.55 times 100, and that's sure as heck a lot greater than 5. Okay, it's 55, and n times 1 minus p, this other one here, alright, would be 0.45 times 100. It's obviously a lot bigger than 5. Alright, it's 45. Both of those are greater than 5. Looking at an example, and we're going to use some technology here to facilitate this example. Assume that 55% of people in country X have blue eyes, so that means population proportion is 0.55. Use technology to illustrate a possible distribution of the sample proportions p hat that may be obtained when 200 different samples, each of size 100, are selected from the population. There we go. Okay, and we've got 200 different samples there. So let's get that happening on our TI Inspire. Just giving the first column here a name, and I'm just going to call it prop blue. Okay, because it means proportion blue, but I've got to spell blue correctly. Oh, okay, there we go. So prop blue. Okay, now for the formula. So leave the prop blue prompt in there because that's going to define it for us. Okay, now we're going to look at randbin, R-A-N-D-B-I-N. Okay, random binomial, and we're going to put in 100 for sample size 100, then 0.55 for p, 200 such samples, close brackets. Now to get that as a proportion we need to divide again by 100. Okay, so we enter that in. You can see all the sample proportions we've got there. Okay, and now we have to add in whoops, sorry, we need to add in one of those. Okay, the data and statistics display page. Prop blue. Ooh, nice. So just making sure you can see the entire thing there in the viewing window for this video, and you can see, yeah, something reasonably normal. There is, there's an outlier to the left, that's for sure, and it does peak really high at the top, but that's the nature of the game. That's the variation, the variability of the data. Let's have a look at it as a histogram. So we hit menu and plot type. Okay, histogram. Nice. Okay, so we can see that it's a little bit skewed perhaps to the left, but it's reasonably normal. We could take further samples as such, get some more data, or even increase the sample size if that's a valid thing to do for the situation. Time to analyze it now. So we're going to analyze the graph and show as a normal PDF. Okay, probability density function. Ooh, alright, now let's move that somewhere where we can read it. How's that? Can you read that? Oh, it went away. It went away. We've got to go to analyze, try again, and doink. Now note the values down there. So we've got the mean and the standard deviation there. So the mean is about 0.55 where the cursor is there, okay? And the standard deviation is about 0.049. Note that. So with this, because we know we can approximate it normally, so using a normal approximation, we can show that the mean mu, which is actually E of p hat, using it in variable form with the uppercase p hat, equals 0.55 based on our formulas for normal distribution. Okay, normal distribution, standard deviation sigma or SD of p hat, capital P hat, okay, is P, which is 0.55 times 0.45, which will be what the brackets come to, over 100, and that comes to 0.0497. Now let's compare. So we've got 0.55, that's very close, and 0.0497, okay, which is very close to that there. So yeah, that's working out fine, isn't it? We have consistency here. So we've got, when the sample size n is large, the sample proportion p hat, when it's the variable, it's capital P, the individual variable. It has an approximately normal distribution. Alright, it's pretty good, pretty consistent, where the mean is equal to population proportion, and the standard deviation is given by that expression there, which we have seen before. Let's look at the last example here. So without having to use technology now, we can quickly see that for 6% of people who have a driver's license in a certain population, using the normal approximation, find the approximate probability that in a randomly selected sample of size 200, more than 65% of people have a driver's license. So the population proportion is 0.6, and that means the mean will be 0.6. Okay, and n is 200, that's a good size. Okay, and so we've got to find the probability that more than 65% of people have a driver's license. Okay, so the mean is 0.6 and the standard deviation 0.6 times 0.4 over 200, over 200, and then we take the square root. I get 0.0346. Okay, so what's the probability in a randomly selected sample that more than 65% of people have a driver's license? So that's when p hat is greater than 0.65. One way of doing that is normal CDF, and we put in our parameters there. So remember, it's continuous, so even though it's bigger than 0.65, we can use 0.65 up to 1, which is the upper limit. The mean is 0.6 and the standard deviation is 0.0346. Probability is about 0.07. Okay, so in conclusion, when sample size n is large, the sample proportion p has an approximately normal distribution with mu equal to the population proportion and standard deviation equals that expression you see there.